Alrighty, so let's read the question and then do a little deeper analysis here. So Fred and Barney are at opposite ends of a 1 kilometer long drag strip in their matching race cars. Fred accelerates from rest toward Barney at a constant 2 meters per second squared, and Barney travels toward Fred at a constant speed of 10 meters per second. How much time elapses until they collide? So we didn't get told which one is which, but let's just, for the sake of discussion, label them F and B. And at some point in here, they're going to collide, right? Will they collide right in the middle? Why not, Martin? Because they're going different speeds. How do you know? Well, one is accelerating. Fred is actually speeding up. Barney's moving at a constant speed, right? But would you agree that they crash here in the middle when their positions are equal, right? When their positions are equal, they are going to crash. So we need to figure out the time when their positions are equal. What is Fred's position initially? On a number line, I guess you could say. 0? Can we just assign any position 0? Sure, why not? But that means then that Barney way over here, he's at position 1 kilometer. But you probably have a feeling that should be in meters, right? So let's assign Barney the position of plus 1,000 to begin with. Everybody with me so far? Okay. So what is Fred's position after he starts to accelerate? Okay. So I'm going to say PF, position Fred, is equal to, well, he starts at 0, right? So we'll say his position is equal to 0 plus his initial position, plus whatever position, or what his, actually, it's 0 plus his displacement, isn't it? Fred's position is the position 0 plus his displacement, and he is accelerating. So PF, he is accelerating. We don't know the time, but do I need to go 0 plus? I can just do displacement. So that's equal to D, which is equal to VIT plus 1/2 AT squared. Fred's position is his displacement, which is equal to VIT plus 1/2 AT squared. Let's fill in some numbers. PF is equal to, well, his initial velocity is 0, so that's nice. 1/2. His acceleration is a convenient 2t squared, so it all boils down to Fred's position is equal to 1/2 of 2 is simply, in fact, just t squared. After all that, Fred's position is equal to t squared. We don't know the time. In fact, that's what we're trying to solve for, right? Now we have to do the same process for Barney. Position Barney. I'm going to move it over a little bit. Position Barney. Now, what position does he start at? He starts at 1,000. And would you agree with me that his position is equal to 1,000 plus his displacement as well? Would you be okay with that? Barney's position is equal to 1,000 plus his displacement. Now, some of you might be thinking, shouldn't it be subtract? Well, the displacement's going to be negative, so I'll take care of that. PB, 1,000. Now, Barney is traveling at a constant speed. So what is his displacement then? When something is traveling at a constant speed, displacement is V bar times T, isn't it? Right? That comes from V bar equals D over T. Position Barney then would be 1,000. Now his velocity is a constant 10, but because it's to the left, we're going to say minus 10t. Barney's position is 1,000 minus 10t. Okay. Now, what did we say way back at the start? They crash, they collide when their positions are equal. So what should we do? set the positions equal to each other. Position Fred is equal to position Barney. And position Fred is t squared. And position Barney is 1,000 minus 10t. And what have I created for myself?
A lot of fun.
I do that daily, Josh. You're right. It's a quadratic, isn't it? Even more fun to be had. So let's write this as t squared. Bring the minus 10t over, and it becomes plus 10t. And bring the 1,000 over, and it becomes minus 1,000. And it's all equal to 0. So I've created a quadratic that occurs when the positions are equal to each other. And can I solve this? Do that with our old friend, the quadratic formula. Or if you prefer, if you've got Desmos or something like that on your calculator, on your phone, like a calculator. Minus b plus or minus b squared minus 4ac all over 2a. And the value of b is 10, so this is going to be minus 10. And that's going to be plus or minus the square root. B squared is going to be 10 squared minus 4. The a value is 1, and the c value is negative 1,000. And it's all over 2a, which is 2 times 1. Are we still good? Everyone with me? Minus 10 plus or minus. Okay, so 10 squared is going to be 100. Minus 4 times 1 is minus 4 times minus. That's going to be 4,000 there, right? 4,000 plus the 100 is going to give us the square root of 4,100 all over 2. I don't have the square root of 4,100. The batteries in my solar-powered calculator are dying. Remember. $64. So minus 10 plus or minus 64 all over 2, which would be minus 10 plus 64 would be 54 over 2, or minus that would be minus 74 over 2. This would be 27 seconds. And this would be, the other one would be minus 37 seconds. But of course, negative time doesn't exist, and so that one isn't really an answer. So our answer is 27 seconds, which seems like a lot, doesn't it? But remember, Barney's only going like 10 meters per second. It's not going very fast. It's like 36 kilometers an hour. Where exactly, it doesn't ask it, but where exactly do they collide? How would we figure it out? Well, the position is t squared or 1,000 minus 10t. This one's way easier to figure out, isn't it? So position Fred would be, what did we say, 27? 27 squared. 576. So actually fairly close to the center. What's the hardest part about this question? Yeah, like the setup, right? Once you get going on it, the math's not hard. It's the setup. If oh, are you? For what number? Sorry. 27. Oh, I put 10 to 24. Nice. 729. Yeah, that did seem off. 729. Thanks. Okay. If only there were another question that we could try to have a little extra practice on this. If only. Thankfully, the author of the textbook was a wise person, and it wasn't me. There's more than one wise person in the world. Now, there's a small difference here, besides the fact that it's a guy named Jack instead of Fred and Barney. Jack is running at 6 meters per second to catch a bus. He sees it start to move when he's 20 meters away. If the bus accelerates at 1 meter per second squared, will Jack overtake it? Will Jack catch the bus? And if so, how long will it take him? So the difference is, in Fred and Barney, they were guaranteed to catch each other, going towards each other. But here, the bus is, oh, they're both going like this, right? If that's the case, Jack ain't going to catch the bus. But Jack is already moving at 6 meters per second, and the bus is accelerating at 1 meter per second in the same direction. Why don't you give this a try? I would suggest use a pencil. See if you can try the setup. I'm going to mark attendance. It's good practice for it. I'm going to show you how to do it in a couple minutes. Okay, so here's the setup. So let's just talk about, again, Jack catches the bus when the positions are the same, right? So what is Jack's position? Well, he starts at position 0, so his position Jack, PJ, 0 plus displacement. He's traveling at a constant speed, so that's V bar times T. The 0 disappears, the constant speed is 6, so position Jack is equal to 6T. What about the bus? Well, the position bus is, the bus starts at position 20, so it's 20 plus the displacement, 20 plus D, and the displacement is VIT plus a half AT squared. The initial velocity of the bus is 0, so it's going to be 20 plus 0 plus 1 half, the acceleration is 1 t squared, or 20 plus 0.5 t squared. And once you got there, steps are the same, just do what? Set them equal to each other. Six t is equal to 20 plus 0.5 t squared. And am I going too fast? Am I too far ahead? Okay, so let's keep solving. Do you guys care which side the t squared is on? Most people prefer the number in front of the t squared to be positive, just because. So let's go 0 equals 0.5 t squared plus 20t. No. That's the 6t that goes over there. 6t, that's 20 plus, so that would be plus 20. Right? That step is crucial, that your signs are right. So if you're having problems later, double check that part is right. So now x equals minus b plus or minus the square root of b squared minus 4ac all over 2a. Minus b, that's a minus 6. 6 plus or minus square root b squared is good. Now, do I need to go minus 6 squared? You should, but it's the same as 6 squared, right? So, I mean, if you want, you should be able to really do it in your head, right? Can I just do that? 36. 6 squared is 36. Minus 4ac, so that's going to be minus 4. The a value is 0.5, and the c value is 20, all over 2a. Oh, so I guess that would be 2 times 0.5. Okay, so 6 plus or minus the square root of 4 times a half is 2, times 20 is 40, so that's going to be 36 minus 40, or uh-oh. Whoa, did I make a mistake? What does this mean? It means that there's no solution. So in other words, you go back to the assumption that the positions are the same, which means that is not true. In other words, Jack does not catch the bus. Every single time I do this question, poor Jack does not catch the bus.
You probably ran out of breath. And he lost the bus.
Yeah. Well, he's only running like he's only running 6 meters per second, right? And the bus is accelerating at 1 meter per second squared. So that means that every second it's going faster and faster, right? For him to go the 20 meters, that's going to take him a little over 3 seconds, right? So if he's lucky, he's going to have to catch it within 4 seconds. Well, how fast is the bus going after 4 seconds? It's going 4 meters per second, right? So he's still going faster than it, but remember there's a 20-meter head start, right? Now I've actually had kids actually try to figure out where's Jack after 1 second, where's the bus after 1 second, where's Jack after 2 seconds, where's the bus after 2 seconds, That's how they want to solve this. Okay, that only works for if they happen to catch the bus on an integer value of time. So yeah.
What if the bus has to stop at a stoplight? There you go.
Every 500 meters, he stops at a stop sign.
Yeah.
Possibly, yeah.
Jack could get very tired.
That's true. Maybe Jack can't maintain a 6 meter per second speed. 6 meters per second, that's like 24 kilometers an hour. I mean, Austin might be able to run that fast, but yeah. Like, how fast would Usain Bolt be running at top speed? In meters per second, you think? I mean, it's a 100-meter race. He does it in less than 10 seconds, so approximately 10 meters per second. That's world-class time. Jack's in his suit carrying a briefcase. You know?
Doesn't look like he's carrying a roof.
Are you sure? He's definitely wearing a suit. Looks like maybe he's carrying his lunch or something or other. I don't know. Okay, so once again, in the textbook, there are some questions on page 64, number 1 to 3. Page 73, numbers 33 all the way to 66. Leaving out 50, 54, 55, and 60. And I will tell you this, on the test, there is a Jack catching the bus or Fred Barney style question. Okay? So, I'm going to give you the rest of this time. Tomorrow, I'm going to give you the pre-test. You should be doing some problems. Hopefully, you've gotten some done. Make sure you've gotten to at least the grade 12 ones, right? Do some problems. Get better at this. We'll reevaluate tomorrow whether I'm ready to move on or not. But for sure, Monday, I'll be starting with vectors if I don't start Friday. No, Tuesday.